All right, first up for today, we're going to talk about the number e. E is a number like pi. It's an irrational number, which means as a decimal, it's a non-repeating, non-terminating decimal. In terms of fraction, it cannot be written, in terms of a fraction form, it cannot be written as a quotient of two integers. What we're going to look at first is a classic way that you can approximate e. So if we take this expression here, 1 plus 1 over n, raise it to the n power, and put in increasingly larger values of n, the values we get back are going to come closer and closer and closer to that value of e. Now, one approach we could take for completing this table is we could, in our home screen, be typing in each one of these expressions. So, 1 plus 1 over 1, raise that to the first power, we get 2, and it's saying specifically 5 decimal places. And then keep changing the value of n over and over and over again until we get all the boxes filled in. A more efficient way that we can do this, as long as we're using technology, let's use it to our maximum advantage. Let's go to y equals and type that expression in y1. So open parentheses, 1 plus 1 divided by, and in function mode we have to use x as a variable. Raise it to the x power. We'll go to our table set, which is the second function above window. Put it to ask auto, and then when you go to table, oops, I didn't want to do that. Sorry. When you go to table, finish this up. It allows you to type in particular x values that you're interested in evaluating the equation for. So the next one is we want f of 10, and then 100, and 1,000. So it's 3 zeros. And then 10,000, so 1, 2, 3, 4. And 1, and then 5 zeros. 1, 2, 3, 4, 5. And 1 and 6 zeros. 1, 2, 3, 4, 5, 6. Now, one thing that you might notice, or you should be noticing, is my column here with y1 is only showing us 4 decimal places. Well, the instructions are specifically calling for 5. So what you need to do is put the cursor on the number itself that you're interested in, and then you see down here, it gives you more decimal places. So we're evaluating it at 10. It's going to be 2 point, and then 1, 2, 3, 4, 5. We have to go up to the 4, and that stays at a 4. And then for the next one, we're at 2.7048, and then the 5th decimal place is going to stay at a 1. And then 2.7169, and it stays at a 2. 2.7181, that's going to go up to a 5. 2.7182, that has to go up to a 7. And then 2.71828, that stays at 8. All right, so you see we jumped from a 2 to a 2.5, a 2.5 to a 2.7, 2.7 to 2.71. What's happening is, as this number gets bigger and bigger and bigger, it reaches the point where this doesn't change. So what if we put in 1, and then it didn't ask us for it, but what if we did 7 zeros? 1, 2, 3, 4, 5, 6, 7. 1 and then 8 zeros. 1, 2, 3, 4, 5, 6, 7, 8. I think I might have done 9, but you get the point. In the 4 decimal places, it hasn't changed at all. The 5 decimal places, I think it'll stick to that 0.8 and never get any bigger. So no matter how big of an n we plug in, we reach a limiting factor. Okay, that limiting factor is our E value. All right, E is located in two different spots on your calculator. Quit out of that. If you just want plain old E without being raised to an exponent, it is the second function above the division sign. If you push equals, you can see it there. Typically, in most problem-solving situations, E gets raised to some exponent. So E to an exponent is the second function above the ln, which is the natural log, which we're going to get to soon. So if you just want E to the first, it's that same number. All right, next thing I want to show you is a feature of the calculator that you may not know about. If you go to the mode button, that third option down where it says float 0, 1, 2, 3, blah, 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 what that will do will be to tell your calculator to round off calculations in your home screen to a certain number of decimal places. So for example here, we have to go to 5 decimal places in order to answer the rest of these questions. So if you have an assignment where you're constantly rounding to the same number of decimal places, you can set that float, in this case, to 5. I'm going to quit out of there. And now when I hit that E button, you see it rounded it to 5 decimal places. Now, you would think that that would do that in a table as well, but it does not. For whatever reason, limitations of our calculator, if you set the float to 5, it's still going to put all the decimal places in the table. So that particular feature would not done us very good based on what we did right here, or the method we used to do that. But for the purposes of answering a couple questions on this page, it's useful. I'm going to skip over this for a moment and go to these two guys. Now, before there was technology available to us in order to get very quick, fast approximations of decimal numbers like this, people would have to come up with other ways of doing that. So these are two ways that you could approximate E pretty accurately, I believe. So if we type this in, 2 plus, we'll have to get that numerator in parentheses, 54 squared minus 41 squared, close those parentheses, and that gets divided by 80 squared. And to 5, nope, it's not as close as I remember. I thought it was a little closer than that. 2.19297. So, something doesn't seem right about that. I thought it would have been, oh, it's plus 41 squared. I was going to say, I thought I remember this being a better approximation. Typed it in wrong, or read it wrong, one of the two. Yeah, that's the number we want. So to 5 decimal places, that approximates pi. I mean, not pi, E. Okay, another one, 3 minus root 5 divided by 63. And again, that approximates pi to 5 decimal places. You're not responsible for these on quizzes or tests, just kind of numerical curiosities of somebody may be thinking somebody had way too much time in their hand back in history in order to come up with those two guys. All right, now this is a little preview of something that's going to be pretty important to us later in the course and the beginning of calculus next year for you guys. Okay, a way that we can express what we did here is we let n go to infinity. Now, we didn't go all that close to infinity. We went like 9 zeros or something like that after the 1. But in theory, if this could go to infinity, then that limit would equal 8. Now, we're going to do a unit specifically focused on limits a little bit later in the year. With our COVID pacing, I'm not quite sure exactly where it fits in. And traditionally, in any Calculus 1 class, that's Chapter 1 is limits. If it's not Chapter 1, it's Chapter 2, where they call Chapter 1 your prerequisite skills. but that's your first topic in limits. So what we're going to be doing later in the year is preparing you pretty well for your first chapter of calculus, whereby you'll have a really good foundation going in. Because learning limits in the context of calculus, having never seen it pre-calculus, can be pretty challenging. So it's definitely an academic advantage to have seen it in our class. Okay, revisiting one of the types of problems we did yesterday. Okay, how would a base E play out in the equation solving that we did? So whether it was a base like 5 or 7 or some of the typical ones we did yesterday or E, we can still use the basic strategy. If we can get both sides expressed in terms of powers of the same base, so in this case, we can rewrite that as e to the 1/2 power, set the exponents equal to each other. Doing this without a calculator, my preference would be to multiply through by the 2 to clear out that fraction, and then solve what's left. Same as we talked about yesterday or the day before, I don't remember the sequence of events at the time of making this video. These have very low risk of extraneous solutions. We don't have to check that for extraneous. Okay, so for number 2, you have to bring that guy to the top. Set the exponents equal to each other, and then we get a little bit of a variation that we didn't see yesterday, where we need to incorporate a little bit of factoring. So we end up getting 2 solutions to this guy, x is positive 3 or negative 1. All right, next problem set right here. We are going to take a look at another way that we can use some of the properties that we use for equation solving. Okay, this group here is from your textbook, and what we're going to do is use the properties of exponents to determine which functions, if any, are the same. So for number 79, we have f of x is equal to 3, x minus 2. G of x is equal to 3 to the x minus 9, and I don't know how much room I'm going to need here. I'll hold off on that one. Copy another one for a second. Actually, let's put it underneath. G of x equal to 1/9 dx. All right, that's pretty basic. That one we could do 3 to the x minus 3 squared. But after we do that, there are no rules for exponents that allow us to rewrite that in any meaningful way for what we're doing here. This is the one we want to concentrate on. 1/9 is 3 to the negative 2. And then multiplying the bases, you add the exponents. And what we can see after we do those 2 moves, copy that wrong. What we can see after those 2 moves is this guy and this guy are definitely the same. So that one and that one are the same. So the last thing we'd have to investigate is, are these 2 the same as that, or are they different functions? Well, we haven't talked about it formally, but this will be a lesson coming up soon. I don't recall again where it falls in the sequence. If we think about the parent function here of 3 to the x, 3 to the x is a basic exponential growth function, which you definitely did in Algebra 1. You did it in Algebra 2. Whether or not you remember it, you're going to have to in the near future when we formally revisit this topic again. But anyway, you should know that that function shifts 2 to the right with those 2. Okay, here, that minus 9 takes that function and shifts it down 9. So although algebraically we can kind of make a pretty firm statement that these two are not the same as that, if we think about it graphically, that definitely confirms the fact of if we were to graph these guys and graph that guy, they're not the same graph. All right, let's take a look at number 80. So we have 4 to the x plus 12. We have 2 to the 2x plus 6. And we have 64 to the 4x. Okay, which ones of these guys, if any of them, are the same? Well, we can get that base 2. So that's 2 to the 2x plus 12. Little line here. This is already base 2. And this one here, 64 is 2 to the 6th. Little brain freeze there. Yeah, 6. That's 2 to the 2x. So this is 2 to the 2x plus 6. So that one and that one are definitely the same. G and H are the same function for number 80. Now, are those two the same as that? Well, algebraically, there's no way to turn either one of those into that. There's no way to turn that into this. Okay, if you think about it graphically, these guys are going to be a basic exponential growth, 2 to the x, with a stretching and a shifting, left to right. Here, we're looking at a basic exponential that's going to be shifted up 12 units. Okay, there's no way that shifting the 2 to the x up 12 units is going to produce the same graph as those. So again, we're going to formally talk about graphing a little bit later, but we can use it to help us along here, at least with some basics that we will remember from a previous math class. All right, number 81. We got 16 times 4 to the negative x. We have 1/4 x to the negative 2. And we have 16 to the negative 2x. All right, well, it's looking like, draw this in here, we can go everything base 2. So that's 2 to the 4th times 2 to the negative 2x. So that's 2 to the negative 2x plus 4. This is 2 to the negative 2 to the x minus 2. It's 2 to the negative 2x plus 4. Well, those guys are the same. This is 2 to the 4th times 2 to the negative 2x. That's 2 to the negative 2x plus 4. Turns out all three of them are the same. So 81, all three are the same function. All right, what about 82? Okay, 82, based on algebraic manipulation of getting bases to be the same, there's not a whole lot we can do with this. They're already base 3s, base e's rather. We can't get that to be a base e. If you try to make any of these look like any of the others, it's probably not going to happen. Let's try a couple things that would be worth exploring. So for example, with g of x, e to the 3 minus x, we could rewrite that as e to the 3rd over e to the x, reverse engineering the subtracting of the exponents. So in terms of graphically speaking, we don't have any knowledge of what that graph would look like, so we can't use that as a strategy. But it's another way we could rewrite it. For h of x, we have a negative, and I'll separate that to emphasize that it's not in parentheses with the e. And then we can do a negative, and then e to the x over e to the 3rd. And if you have a negative sign in front here, does that turn this into that? No, it doesn't. The only thing that would be a possibility is if we raise that whole thing to the negative 1 or that whole thing to the negative 1. So it turns out that none of these guys are the same. And showing that none of them are the same with algebra, well, how do you know when you can stop trying? It's a little bit tricky. And as far as the graphing stuff with the approach there, it uses a little bit more than you're going to remember from Algebra 1 and Algebra 2. So we're not even going to go there with those. All right, that is a wrap for today.